your respective places. So this session is so it is just one minute is yeah. Okay, so I hope you all can hear me, right? Okay, yes. Okay, so I hope that you all are safe at your respective places. What I'll do is I have received some questions from some of you. You have posted some questions in the forum and also sent some questions personally to my email. So I have just made the list of all these questions. I'll just address those questions first, and then meanwhile, as the session goes, you can post your question in the live chat box. So if time permits, I will address those as well. Okay, so first let me share my screen. Yes, so I hope you can see my screen, computer screen. So one of the common question that I have received many times from many of you, one confusion that when you have a stiffness matrix, it is either local stiffness matrix or global stiffness matrix. Global stiffness matrix means once you assemble all the local stiffness matrices based on their connectivity. So when you assemble them, so both the stiffness matrices are singular. Are singular mean that if you invert those stiffness matrices, then their determinant is zero. So these matrices are singular. What is the reason for this? So just to answer, these are very interesting property of stiffness matrix. You see, what is stiffness matrix? When we write Ku is equal to F, you take a Ku is equal to, you have a physical system, and then that physical system is represented through an equation Ku is equal to F, right? So Ku is equal to F. This is the mathematical representation of that physical system, where the U is the displacement and F is the force vector and K is the stiffness, right? Now, stiffness is the property of the structure. F is the external load applied on the structure. Now, what you see in the structure, in the physical structure, same thing should get reflected in this equation. Okay. Now, take an example of any structure. For instance, if we take a beam like this, okay, and it is subjected to some load. Now, this is an unstable structure because see, everything in a three-dimensional space has some degrees of freedom, right? Now, what happened? In order to make a structure stable, you have to provide some constraint. You have to restrict some degrees of freedom. Now, if you do not restrict the degrees of freedom, then what will happen? The structure will become unstable. When you write, for instance, this is the truss member, and this is the stiffness matrix of this truss member. Now, if this truss member, if we try to invert this stiffness matrix, the inversion will be zero. Determinant of that matrix will be zero. Now, this truss member is still unstable because we have not. It has total 4 degrees of freedom. 2 degrees of freedom at joint number 1 and 2 degrees of freedom at joint number 2. Total 4 degrees of freedom. But then, among this total 4 degrees of freedom system, if you do not constrain any degrees of freedom, then what will happen? The structure will become unstable, and that this instability, the structure is unstable, that gets manifested in the stiffness matrix. So that's why the stiffness matrix is 0. Now, if you determine the rank of the stiffness matrix, you will see that, for instance, if we take another the beam problem. Okay. Now, again, in the beam problem, see, if you try to invert the stiffness matrix, this determinant of this matrix will be 0. In order to make this structure stable, for instance, you have to provide at least 3 constraints, two rotation, 2 translation and 1 rotation. Then only the structure become stable, and this is to be implemented in the stiffness matrix. So that constraint to be applied. If you do not apply that constraint, the stiffness matrix, the structure is unstable. Now, suppose if I provide 2 constraint, one constraint is 2 constraint, means 2 degrees of freedom is restricted. One is horizontal displacement, one is vertical displacement. Then, but still this member is unstable, because we have to provide a vertical. We have to provide 1 constraint at this joint. Now, if we provide 2 constraint, 1 and 2. So row number 1, column number 1 will go. Row number 2 and column number 2 will go. Then we are left with stiffness matrix 12 EI minus 6 EI by L square by L cube, and then this is minus 6 EI by L square, and then 4 EI by L. Okay, now you see this matrix is so what we have to, in order to make this entire structure stable, we have to provide at least three constraint, right? Now, so now next is another question I received frequently is internal hinge. Suppose if you have an internal hinge, what is the question is, and what is the degree of freedom of an internal hinge? Suppose we have a hinge here, we have a roller here, then if we provide an internal hinge. Now, what is the degrees of freedom? Suppose if the structure deflects, then the deflected shape of the structure will be something like this. Hinge cannot take any rotation, so this will be something like this. Now, what are the degrees of freedom? What are the additional this displacement field that we have to determine? This is one angle, this is say theta1, this is another angle theta2, and then this displacement, right? This displacement. So these 3 additional unknown is introduced in the system, so that needs to be determined. Now, another question I received is how to number the joints and member to avoid rearrangement in matrix. Yes, suppose if we take the example of same question, same problem, example the same thing. Suppose if we have a system, if we have a beam member like, take this one, okay. If you have a beam member like this, instead of, what I have done is, suppose you have your beam is something like this. This is hinge and this is roller, right? This is roller. Now this is subjected to some load. Now you have 2 degrees of freedom here. So U1, U2, and here it is U3 and U4. U1 and U2 is equal to 0, and here U3 is equal to 0, right? So U4 is unknown. Now your stiffness matrix. So since U1, U2, and U3 are unknown, then in this stiffness matrix, this is the stiffness matrix. In this stiffness matrix, you can just remove 3 rows and 3 columns. First 3 rows and 3 columns. The only stiffness of the system, you are left with 4EI by L. So partitioning is now easier. You just remove the first 3 rows and first 3 columns. While you partition it, that partition you don't have to do the rearrangement between columns and rows. But instead of numbering like this, if I provide দেখো আমার কথা শুনতে পাচ্ছ?
Okay,
Hello?
fine, sir. Fine, sir. Fine, fine, fine. Fine, sir.
Audible now, right?
Okay, yes, yes.
Okay, okay. Okay, once again I'll share the screen. Now it is live, right?
Yes, yes, sir.
Okay. Sorry for these all these disturbances. It seems there was some problem in the audio, so I had to disconnect and connect again. I really don't know how much you could hear. What I'll do is I'll just again start from the beginning. Some of the questions I already discussed, but let us discuss them once again. See, one of the common confusion that I have received through several of you is why the stiffness matrix, either local or global, is not invertible. Like, look at the stiffness matrix. If you try to invert it, then this is, you will see that its determinant is zero. Now, what is the stiffness matrix? What is, when you write Ku is equal to F, K is the stiffness matrix, this is the stiffness matrix, and U is the displacement vector, and F is the force vector. Now, what happens? K is the property of the structure, right? Now, whatever you have in the system, in the structure, that should get represented through this equation, right? One thing what is missing in this structure is, you see, every system, I'm talking about a physical system, every body in a three-dimensional space has 6 degrees of freedom, right? Now, in this case, for the truss member, we have 4 degrees of freedom, 2 degrees of freedom at each joint. Now, we cannot allow a member to have all its degrees of freedom. If we do so, then the member will become unstable. The structure will become unstable. You have to provide some freedom in the form of support, right? But that information you have not included in the stiffness matrix. This stiffness matrix, what information is there? It is there only the geometric configuration, material property, that's it. But the support conditions, this stiffness matrix, as if there is no support provided in this system, there is no constraint provided in this system. That's why the structure is unstable, and that is manifested in this equation by a singular stiffness matrix. Similarly, if you have a truss problem, you have a beam problem like this. In beam problem as well, you have all these degrees of freedom. If you allow all these degrees of freedom, 1 2 3 4, then you will see that this structure is unstable. So you have to restrict some degrees of freedom. Now, when you restrict degrees of freedom means, then you have to partition the stiffness matrix. You have to partition it like what are the known displacement, what are the unknown displacement, and then from that partition you have to calculate the unknown displacement. That's the reason why the stiffness matrix is not invertible. For instance, if I give you a truss member in a local coordinate system, um, you give a truss member in the local coordinate system, then if you see, if you recall, the stiffness is AE by L minus plus 1 minus 1, then minus 1 1. You look at the stiffness matrix is inverted. This is the determinant is 0 because there is no information about the support condition in this. Now, if you restrict this one end, means the one end is restricted, then it is not, it is invertible. So that's the reason why the stiffness matrix is singular. You have to provide the information about the constant. Internal hinge, another question was what is the degrees of freedom in an internal hinge? You see, it is an internal hinge, and if it has to deform, then it will deform like this. But then this is theta 1, this is theta 2, and this is delta 2. So we are providing three kinematic indeterminates, or the variable we are providing when you provide a hinge here. So this theta 1, theta 2, and delta needs to be determined. That's why this is 3 degrees of freedom. Now, another question is how to member the joints and member to avoid rearrangement of matrix in later stage. This is a very important. For instance, when you take the example of this example once again. You see, when we write stiffness, what we do is, suppose you have a member, and then this is your 1, this is 2, this is 3, and this is 4, right? And then similarly you have 1 2 3 4 and 1 2 3 4. Now suppose you provide constraint like this: u1 is equal to u2 is equal to 0, and then u3 is equal to 0. Then only unknown u4 you need to determine. If it is only unknown here, then the partitioning can be done just simply like this: first 3 rows and first 3 columns will move here, and then last rows and last column will move here. So partitioning is easier. But then if you number this way, suppose if you provide constraint u3 is 0, suppose u3 means your displacement in this direction is 0. But if you number in this way, this is 1, this is 2, and this is 4, and this is 3, then what happens? Your u1 and u2 is equal to 0, and u4 is equal to 0, and u3 you need to determine. Then in that case, what we have to do? We have to move u4 here, u3 down, and then 4 here, 3 down. You have to do this rearrangement in columns and between columns and between rows, and then do the for partitioning. So yes, numbering of the nodes and members are important. How much your computation required, because its consequence is how you get the stiffness matrix, whether you get the banded stiffness matrix or not banded stiffness matrix, what are the how many off diagonal terms as non-zero. It depends on your numbering system. So numbering is important. By just changing the number, you can reduce some of the computational effort that you may need in this kind of analysis technique. Transformation: what is local coordinate, global coordinate, and transformation? There is another question. Local coordinate is, suppose if we have a truss, then this truss is the local coordinate, right? Your local, according to local coordinate, this is suppose u2 and this is u1. But then your global coordinates is x and y. So if a truss is like this, then your displacements are defined with respect to this coordinate. Here your displacements are defined with respect to this coordinate. And here so in this member, your local coordinate will be this. Local coordinate may be this, but the global coordinate is this. Similarly, take a beam. If you have a beam like this, you have determined what is the stiffness matrix for a beam. But then when you are solving a frame problem, then you see this beam is oriented horizontally, this is vertically. So for this beam, this is the local coordinate. For this beam, this may be the local coordinate, this is the local coordinate. But then global coordinate is x and y. So you determine for the element stiffness matrix with respect to the local coordinate, then do the transformation of this matrix to get the matrix in global coordinate, and then you assemble them to get the global stiffness. This from local coordinate to global coordinate is done through the transformation matrix. Transformation matrix depends on this theta, how it is inclined with respect to your local coordinate system. So and the global stiffness matrix become T transpose K local and T. Okay, so this is how the local and global coordinate system comes in. Now, then another question is what is the question pattern in the exam? The question pattern in the exam will be very same as your all the assignments that that you have done. It will be very similar to that. Another question was, many students were asking that how to get Scilab, the software. The software is available. You just Google Scilab. It will take you to the Scilab webpage, and there you can download it. Ideally, if you have access to MATLAB, you can try with MATLAB. The only reason we explore Scilab is because that was free, and all of you can download and use them. Okay, but it is available. Yeah, you can download it. Another question that I have received is related to assembly. How the assembly to be done? See, when you do the assembly, as far as theory is concerned, you will see matrix method is not is understood, right? But then implementation is very important. Assembly is like this. Suppose you have a truss like this. You have a truss like this. and then you have a truss. All these are hinge, and then you have some support here, right? Now suppose degrees of freedoms are right, this is 1 and this is 2, this is 3 and this is 4, this is 5 and this is 6, right? This is member number, say member number 1, member number 2 and member number 3. This is how the members and joints are suppose numbered. Now the stiffness matrix of each member will be 4 by 4 stiffness matrix. Suppose K1 will be your a 4 by 4 matrix where degrees of freedom will be 1, 2, 3, 4, and this is 1, 2, 3, 4. Similarly, K2 will be again 4 by 4 matrix where degrees of freedom will be 3, 4, 5, 6, and then 3, 4, 5, and then 6. Similarly, K3 will be 3 by 3 matrix, which will be 5, 6, 1, 2, 5, 5, 6, 1, 2, 5, 6, 1, 2. Okay. Now, when you globalize it, when you assemble them, assemble stiffness matrix will be here in this case 6 cross 6, because 2 degrees of freedom per node, and then 6 degrees of freedom total 1, 2, 5, 1, 2, 3, 4, 6. So first what we do is we make a 6 by 6 matrix where all elements are 0. All elements are 0. All elements are 0, right? Now number them 1, 1, 2, 3, 4, 5, 6, and similarly 1, 2, 3, 4, 5, 6. And now look at this, the connectivity. Now you have 1, 1 here, and then 1, 1 here. So this 1, 1 and this 1, 1 you have to add and put it in 1, 1. Similarly, 1, 2 here, this is 1, 2, and there is then 1, 2 here. This 1, 2 and this 1, 2 you have to add and put it here. And then 1, 3, 1, 3 here, there is no 1, 3, so 1, 3, it will come here. Similarly, suppose you take 3, 4. This is 3, this is 4, this is 3, 4. Similarly, you have 3 and then 4. These 3, 4 and these 3, 4 you have to add, and you have to put according to that particular place. Similarly, if you have many number of such stiffness matrices, local stiffness matrices, you have to assemble like this. Okay, so and in terms of writing the code in Scilab or MATLAB, the demonstration of the code is already done. You please go through the video and see how this is to be written. This is the concept, but how it is to be translated in a code. For that, you please see the video. In exam, whether all questions will be MCQ type, yes, all questions will be MCQ type, but it doesn't mean that you don't need any calculation. You have to do calculations, and the final you have to find out the answer. There will be questions of different marking, so you have to know all these details carefully. Okay, that is very important, even though the questions are MCQ type. Then then another questions transformation matrix is done. Another questions I received that what is the if you go to industry, then how much this method is being used in industry, and this kind of confusion. You see, if you recall all the videos, even starting from the course, very first week, we discuss as all the things, the methods we are discussing, that is mostly for the skeleton structures like your beams, frames, truss, okay, those kind of structures. So now then, you have a structural analysis where you discussed the determinant. You were introduced to bending moment, shear force, and then determinant structures, some methods for indeterminate structures, and then this course is advanced level course, how to analyze the structures which has many members, many nodes, skeleton structures, and then from there you have extension of that, or the more generalized form of this concept is finite element method. If you go to industry where they design buildings, frames like stadiums, they do use this method. Most of these many softwares we have like StatPro, ETAP, they do use this method. Then But then if you are analyzing a different kinds of continuum, like you are analyzing a dam, you are analyzing an aircraft, a ship, a foundation, okay, which are not a skeleton structure, then there you need have a more generalized form of this. For that we had a very brief introduction on finite element method in the last week. Okay, yes, it is used in the industry. Then another question I have received is that the confusion in stiffness. You see, when we say stiffness, had it been a spring, just a spring. Suppose you have a spring, and then you have a force and displacement is say x, and this is your strain constant, and then we can write that F is equal to K into X. It is just one stiffness K. But then when you talk about stiffness in a multi-dimensional case where you have many degrees of freedom, then it is no longer a scalar quantity. We have seen in this case we are dealing with we have dealt with the stiffness matrix. It is just not a stiffness. Now then, in that stiffness matrix there are many elements. Okay, now every element. So when you talk about a stiffness matrix, essentially we are talking about collection of several stiffnesses. Okay, means when you a two important term is stiffness is defined by load per unit displacement, right? Load required to have unit displacement. This is stiffness. Now then, two important concept here. Two important parameters: which displacement we are talking about and which force we are talking about, right? Now, for instance, say a simply supported beam, then in a simply supported beam, if we apply a load here, then it will deflect, and then if we apply a moment here, then also it will deflect, something like this. Okay, it will deflect somewhere. Or if you apply a moment here, suppose if you apply a moment here, then it will deflect like this. Okay, now in this case, suppose this is your theta and this is your p. So when you are talking about this force and this is your force and this is your deformation, then you have one stiffness. But then when you're talking about this is as your force I'm talking in a general sense, it could the force and moments both, and this is your displacement, then your stiffness will be different. So when you talk about stiffness, it depends on the context that which force and which displacement you are talking about. Another question I have seen is where these stiffness quantity, these are not same dimensions. Like here it is 6 EI by L square, here it is 4 EI by L, and then here it is 12 EI by L cube. The dimensions are why the dimensions of stiffness are different. The dimensions of stiffness are different because you have Ku is equal to F. Ku is equal to F. You cannot look at the only dimensions of the individual element of stiffness matrix. You have to see when they get multiplied with the corresponding displacement, they get the dimension of the force or not. That is important. Now in the displacement field, you have displacement, rotation, which is having different dimensions, but those different dimensions quantity need to be multiplied with something to get the force dimension. So naturally all the quantity dimensions will be different. So we have to look at the dimensions of K and U, not just the stiffness. Okay. And okay, no other questions in the live chat box. Okay, so these are the questions I have received. Some of the questions received from forum and some to my personal email. So we have time restrictions, so we need to stop. But then, if you still have any questions, I request you to type it in the chat box. What is important here is please note that just by looking at it, going through this theory may not help. You have to really translate them. This is very important. If you do not translate them, if you do not write the code, then probably things will not be very clear. So with this, I hope if you still have any questions, and then you please you can write on the forum. The Google sheet is also given to you. You can still write in the Google sheet, and then I can communicate with you either by email, or I can write all these, respond to you in the forum. So with this, I thank you all. So I hope you are enjoying the course, and doing the assignments. And just one piece of advice, and then I'll close. Going through the close only will not help. Please, you have to go through books. You have to read it. Course is just whatever given in the existing literature is a very concise form of that. But to get a real feel of that, you please read books and write code, and then try to see how this method works for different kinds of problem, and then compare the potential and limitations of the method vis-a-vis the methods you have learned in structural analysis 1 and you'll be learning in final element method. With this, thank you. So Shumuto, I am just stopping here.